Test criteria there, and it's exercise 7G. And here we go. A Leslie matrix is used to model growth. So let's take the following situation. So we're going to do it without Leslie matrices. I'm going to show you how you can do it with Leslie matrices. You're going to get a feeling initially doing a projection of a year or two, it's to do it without Leslie matrices. And as always with maths, the idea is, well, will this make our life easier if we have to make a 50-year projection? And the answer is yes. And with one single calculation, there's just a bit of setup at the start. So example 1 is this. A population of bilbies has a lifespan of 5 years. Thus, they're either 0, 2, 3, or 4 years old. The following table gives the birth rates and survival rates for each age group. So my first question, what does this mean? Oh yeah, and by the way, I have no idea about lifespans of bilbies or anything like that. I just literally made it up and bilby came to mind. What does this information mean? Birth rates and survival rates. So 0-year-old bilbies don't give birth to other bilbies, and 90% of them survive into their first year. Okay? 1-year-old, they give birth to 1.2 bilbies per year on average, and survival rate as well. 2-year-old bilbies give birth to 1.3 bilbies per year on average, and they have an 80% survival rate. 3-year-old bilbies give birth to 0.6 bilbies per year on average, and they have a survival rate of 30%. In hindsight, I wish I had never used bilbies with birth rate because I'm really struggling to say it. Anyway, here's an important first one, mate. With population growth, any question like this, and this is that don't forget, you will only deal with populations of females within the species because they're the ones giving birth. Because the males aren't giving birth, it creates confusion, but you work on the assumption that once you've done that forecasting, you double the population based on that assumption. Is that right? So you want to consider whether you need to double the population again.
So is that data just purely for
This is going to be just females. Yeah.
Okay.
Question 8. In a new breeding enclosure, the initial population is 10 for each category. What is the population after 1 year and after 5 years? So let's do the 1 year, and then we'll talk about the 5 years. So if I just scroll down here, and what I might do is I might just, actually no I won't. Oh yeah I will. I'm going to grab this table and just blood straight off it. So I'll copy that, paste that there. This table is going to help us. I'll rub out all these birth rates and survival rates. It's a little bit morbid. We talk a lot about mortality, survival rates, all that kind of stuff. So forgive me now. And let's say age 1 and age 5. Oh, actually, I might create age 0, age 1, and age 5. And at age 0, we've got 10, 10, 10, and 10. That's what the question says. Initially, the population is 10 in each category. So now what will be the population in each category based on those birth rates and survival rates for 1 year? You're on the right track. Let's start with survival rates. So if 90% of the 0-year-olds survive, what does that mean? 9? Does it mean 9 here? Excellent. They're 1 year older now, so they're there. And 9 of the 10 1-year-olds survive to be 2-year-olds, and 8 of the 10 2-year-olds survive to be 3-year-olds, and 3 of the 10 3-year-olds survive to be 4-year-olds. Happy? And then, how many 0-year-olds are there? So there's 10 times 1.2 plus 10 times 1.3 plus 10 times 0.6. That's the birth rate for 1, 2, and 3-year-olds. And that gives 31. I hope you can see. So in total, there are 40, 57, 60. So the population's gone from 50 to 60. Population growth won't follow an exact exponential model though. So under a Leslie model, particularly if you've got a split like this, if we've got we might have a large group like this now, but because these groups will decrease, the 0-year-olds might be less next year, and you might get this population growth and then we settle back down to some other value. So it takes a while for it to settle. Is everybody comfortable with where we're at there? Here, if we were going to do this year by year, next year, we're going to get decimal numbers of bilbies, and we have to do appropriate rounding. And you'd have to ask yourself the question, do I keep the decimal number as I forward forecast to year 3, year 4, year 5, or do I round each time? And it's probably going to depend on the situation. I would say you'd want to keep the decimal number as long as you can, and then round at the appropriate junctures, but it is going to depend on the situation. How about 5 years old? How are we going to go with that? But then they step down each year, don't they? So you're not doing 0.9 times the same number 5 times. That's the problem. And as they step down, the 0.9 changes. Jamie? We're going to use, so we could do, to be honest, we could set up, we do that. We could set up 2 years, we could set up 3 years, 4 years. It wouldn't actually even take us that long. It's a small population thing. This can be much more complicated when it comes to humans, for example. Ours up, let's say we have a lifespan of 0 to 100. We might be able to calculate those survival rates and birth rates, but then do you want a 100 by 100 matrix or a 100 by 100 table? Do you set it up in 5-year groupings, maybe 10-year groupings? Is that a fair representation? There's a lot of assumptions involved in that. So let's consider this in love. So here's my matrix. For this particular case, where we've got five age groups. So I've got a population matrix. This population matrix represents the number of 0-year-old bilbies, the number of 1-year-old bilbies, the number of 2-year-old bilbies, etc., etc. And then I have this. This is the Leslie matrix right here. I keep on walking away from my laptop and I'm recording, aren't I? Let me not forget that. Right, I'm back. This is the Leslie. And if we multiply this population matrix by the Leslie matrix here, you put the population matrix on this side, we get birth rate 0 times by population 0. And you know the birth rate 0 should be, will probably be 0 most times. And then we get birth rate for 1 times by the 1-year-olds. Birth rates for 2-year-olds times by the population of 2-year-olds. And this will create our top cell of our resultant vector, which will be our population afterwards. So this is how we develop our Leslie matrix. I'm just telling you now that is what's created. If we do the Leslie matrix times the population matrix, population at year 0, the initial population, we get this, which is the population of 0-year-olds times by the birth rate for 0, population of 1-year-olds times by the birth rate of 1-year-olds, etc., etc. And we get this, 0-year-olds times survival rate. And then that's how many 1-year-olds now have. Does that make sense? You get a diagonal here, so you get all the birth rates along the top. You do get a diagonal, which creates, over the top, which creates a bunch of zeros here in the last column. So it's not quite symmetrical. You've got to be careful. You're not trying to aim to have a diagonal of zeros of survival rates that meets in this bottom corner. It won't. That's 0 there because the survival rate of 4-year-olds is 0. We've seen a 5. And if we want to work out the population in the 5th year, we get the population in the 4th year times by the Leslie matrix, which is and you see what I've done here, down, basically, which is what you were saying, Dylan, but in a bigger form, the population at year 0 times by the Leslie matrix 5 times will generate that 5th year population projection. And then we get this. This is a generalization. And in fact, this stuff in the box is a summary. So this is it. If anybody wants to copy it down now, I'm happy to pause and wait, but otherwise I'm happy to carry on and you can copy it down later. 2 people want to copy it down. Is that a class happy with that? Let's resume. Okay, so example, population bilbies has this lifespan, the following gives birth rates, survival rates, etc. Breeding closure, blah, blah, blah. Find the population after 5 years. I think I've only got one more example anyway, so it won't take us that long. So let's do it. You grab a calculator. You've got all the data written down, I assume. I hope so. Otherwise, it's going to take me a bit of flicking back and forward. So I just got this. Okay. Wait for it to spin around a bit. And change the view because it doesn't like me. That's too big. Okay, so in the calculator, I'm going to go into run matrix and I'm going to set up a matrix. It's going to be a 5 by 5. Well, actually, 5 by 5 is. So I'm going to remove a row. So reset your matrices. And I'm going to exit that and I'm going to remove a column. Now if I exit, it should say 5 by 5, which it does. I'm going to go through and change these. So it's got a 0 birth rate, and then a 1.2, and then a 1.3, and then a 0.6, and then a 0. Is that right? And then it's got a survival rate of 0.9, and then a whole bunch of zeros. And then it's got a 0 and a survival rate of 0.9, and then a whole bunch of zeros. And then it's got a 0 and a 0 and a survival rate of 0.8, and a whole bunch of zeros. And then 0, 0, 0, survival rate of 0.3, and zeros. And I've got that defined now. So I set that there. And then I'm going to go into here. And I'm going to do that Leslie Matrices multiplied by the initial population. And I'll just do it once to check our answer first. So matrix A, and I want to multiply that by a column vector, which is 5 high and 1 deep, and it's got a 10 in each column. Oh, so I can't press enter on here. 10, 10, 10, 10, and I get 319983, which is what we got before. And now if I go back up and reuse that, I put this matrix in brackets, and I want to do that matrix to the power of 5. And there's my population, which I can now round. So which I'll just screenshot back to our OneNote. I'll put that back, and I would make the statement that the population is 0-year-olds is probably 93, 1-year-olds is 59 rounded, 2-year-olds is 39 rounded, 3-year-olds is 18, and 4-year-olds is 6. For the rounding as well, it might be more appropriate to round down depending on the question. Chris? In this case, it's just asking for the population, so it's reasonable for me just to round to the nearest, and that's fine. But if the question might ask you to do something else, I'll actually start this again. Might ask you to consider something else, in which case you might have to round down. Like you might say, when does the population first get to 93 0-year-olds? In which case it wouldn't be appropriate to say this year, you'd have to go another year. What you can also do, so that's the wrong one, is you can go to here and consider happening over time. What does this population head towards? And to do this, just do something inordinately large here, and it will give us a bit of an indication of what's happening with this population. You can see that this population is growing exponentially. So once you get past a few, it will head to what's called a steady state vector. So it might do a bit of this and then standard steady state, and that will be a representation of what those population values are doing, whether it's exponential or whether it's going towards 0. And in a very finite set of cases, it might hit a nice plateau and actually stay reasonably steady at a certain value. Any questions? You can take that answer and you can just write that down, add them up if you need to, or you can multiply that by a row vector of 1s and it would add it up for you. That's enough. Good example 2, consider the release of salmon spawn into a new lake. If initially 100 newborn salmon are investigate the long-term population model given the following birth rates and survival rates. So I'm going to just stop the video and give you a chance to have a look at this and prepare it so you're not mucking around the video watching me calculate a bit. Hopefully you can see that we just need to set up this system. And I have, no, there it is. So my matrix is going to look like this. L will equal the birth rates along the top, 2.1, 1.2, 0.2, and then 0, 0, 0, and then the survival rates, 0.1, 0.35, 0.4, 0.25, and 0.1 with a whole bunch of zeros around it. And we've got 6 age categories, so it should be a 6 by 6 matrix that we develop here. And this gets a bit monotonous, but it happens. We will never expect you to multiply a matrix this large, so I can't think of a case, and again, I don't know what they're going to throw out in the external exam, but I can't think of a case where we'd expect you to do a Leslie matrices using pen on paper methods. So you're pretty much going to be pumping something like this in your calculator. So I've done that. I've got matrix B defined as my Leslie matrices. I've set it. So my population 0 is equal to 100 times 0, 0, 0, 0, 0, 0. No, that's not right. And I would now go through and do the calculation of matrix B to the power of something. What I might do is I might actually not make it the power of 100. Can't. Let's make it to the power of 1 and just check that things are working first. And so, ooh, what's happened there? It would seem so. If I exit out of here and check this out, go down to here, so my mistake must be my defined matrices. I've got. Where's it? Oh, there. Okay, don't ever put random 3s and 2.1s in the corner. It doesn't work. Thanks. Okay, let's try that again. There we go. So 210 of the 210 new salmon, because of the 2.1 birth rate here for the original 100 salmon, but the original 100 salmon has got down to 10, because that's their birth rate.
Why did they die so quickly?
I think, yeah, anyway, not getting into biological discussion. And if I do to the 100, what? 11. Sorry, I'll do 11 in a second. But there we go. It's a growing population. Let's do 11. There's 11. Fun. 458. Now, a couple of things before I stop this video. Firstly, this is based on a massive assumption. The first one being the male-female 50-50 split. We should double these populations if we're finalising a question about total populations. The second massive assumption is this is a growing population. At some point, this water space, lake, river system, whatever, is not going to handle that many salmon. So there's a secondary model that comes in. We are not considering anything to do with predator-prey. We're not considering anything to do with space constraints, food supply, and we're not considering anything to do with migration factors or immigration factors in these populations. So they're closed systems with infinite resources and no predators. That's our assumption. You might have to. You could make them more complex, and they're used in a much more complex way, but you don't need to for this topic. That's it. I'm going to stop the video now, by the way. Bye.